Last time there was a very nice question at the end. It had to do with this derivative operator. And somebody asked me, since L as a vector is not in scri, but it's transverse to scri, so how can the derivative operator, which is just within scri up here, how can it act on this vector? And it's absolutely right. The dA does not know how to act on this vector field LA, but it's a peculiarity of the null surfaces that we have to be very careful about the contravariant vectors and the covariant vectors, or the vectors and the covectors, if you like. So on covector LA, dA does know how to act on it. So dA of LB is in fact well defined, even though dA of LB is not well defined. So this is not well defined. And this is because on scri, we can introduce intrinsically u, theta, phi coordinates, and then we have got n, m, and n bar. And n is just d by du, NADA is just d by du, and MADA is just this complex combination of d theta and d phi, d by d theta and d by d phi. And then the dual vectors are dAu and n bar A is just equal to d theta and d phi, the same combination, so that we have got the relation that if I take this LA times MA, this LA up here that I got, which is given by dA of u times MA, I get 0, and LA times NA is equal to 1, because NA dA of u is equal to 1. And so the statement is that the covector LA is really defined intrinsically on scri, and then the statement is that therefore the dA of LB covector is in fact well defined. By the way, notice that if I look at NA with a covector, that of course is just equal to grad A omega, and because omega is equal to 0 on scri, the pullback of this vector covector vanishes on scri. The pullback vanishes on scri, and so the triad is n, m, n bar, and the co-triad intrinsic on scri is L, m, and n bar, and therefore it knows how to act. And I'll send you these notes today, starting from this page. And there's another clarification, which is really, why is this dA well defined? Remember, the idea was that if you give me any covector Ka on scri, just on scri itself, covector Ka just defined on scri, manifold Ka up here, just defined on scri, then what you do is you extend it to interior of space-time. This is the blue, is an extension in the interior space-time, so that and then you just define dA by the action on this Ka, and then you pull it back. So basically, this was the definition that we had given of dA Kb. Supposing I got two vectors, two extensions of this covector. Supposing I got Ka, which is a pullback of K prime, and Ka, which is also pullback of, the same K is also pullback of Ka up here. So this does not have to be unique, but you can check very quickly that the difference between them is of the type omega times VA, because omega vanishes. Therefore, on scri, this would go away, plus F times Na, because pullback of Na on scri is equal to 0, as I just mentioned. And so the ambiguity in the extension is exactly of this type. So if I now take grad A and operate on the difference between the two, then that is the same as operating on grad operates on omega times V, plus omega times grad operates on V, plus the second term will be grad A F times N, and then grad A F N times F up here. But now you see that this is equal to 0. The pullback of this is 0 on scri. The pullback of grad omega is 0 on scri, because omega is equal to 0 on scri. Omega, of course, is 0 on scri. Pullback of n is 0 on scri. And more importantly, we are in the confound frame, which is divergence free, and therefore this pullback is also 0. And therefore, pullback of all of this is equal to 0, and therefore the pullback of grad A K prime, grad A operating on K prime minus K is also 0. So our pullback of K, grad A of K prime is equal to pullback of grad K, and that is dAKB, so it is unambiguous. So these are the two main, it's a kind of discussions point that we talked about. And then basically at Scry, we have a symmetric group B, and that preserves a universal kinematical structure that is common to all asymptotically flat spacetimes. And we're got a dynamical field D, which varies from one spacetime to another as a potential for the bonding use and a second potential for the radiation field. In stationary spacetime, for example, this D is sort of trivial in the sense that the shear can be made to 0 by choosing cross sections, U equal to constant cross sections, and the news is 0 and the radiation field is 0. But in radiative spacetime, of course, D is non-trivial and these things are not 0. So from one spacetime to another, D changes, and in fact, D carries the information about the radiative content of that spacetime. And now the statement was that we can do a Hamiltonian framework and then calculate the Hamiltonians which generate these symmetries in the BMS Lie algebra. So basically, look at such a transformation, which is made more precise here, namely dAKB for any K is mapped to dAKB plus epsilon infinitesimal version of dA of lead C operating on that minus dA lead C operating on that. So because of this difference, it really just lead C operating on dA. And so the statement is that in Maxwell and Yang-Mills theory, it was the case that if I just take the Maxwell field, for example, and if I looked at F goes to FAB plus epsilon this is an infinitesimal canonical transformation, and the generator gives us the energy, momentum, and angular momentum, depending on what the vector field C you use. You can use the time translation in Poincare group, or space translation, or rotation, and that will give you energy or momentum or angular momentum. Here what we have is really the super translations, which are multiples of n. F is an arbitrary, is a function. It's a conformally weighted function, but at the moment we're fixed NA, so it's just a function. And then we saw, I just claimed and I gave you the reference that similarly we can calculate the Hamiltonian, which generates this transformation for a super translation, and that turns out to be given completely by just a News tensor and this F up here. Oops, I should have there's a mistake here. Sorry, thank you. I just noticed it. Not noticed it before. This is oops. This is equal to sorry. Let me just correct it. It's a mistake. It is linear in F, so it should be NAB times F times NAB, F of theta phi. Let me do it properly. Let me take it out and do it properly. So this is equal to NAB plus so it is given by NAB multiplied by F times N plus 2 NA DADBF. So it is linear in F. Each term has an F alone up here. And then the statement is that the second term disappears if this were a translation. It's the first linear combination of the first four spherical harmonics. And then you just get the flux of the energy momentum to be given by that. And if alpha is equal to just 1, so it is just equal to alpha naught, then in this case, I just put alpha naught equal to 1. Then it's a pure time translation. And then the flux associated with that, NA, because I'm just putting this equal to 1. And you see this is positive, and that is why gravitational waves carry positive energy in full general relativity. And this is important to know, to say that gravitational waves are real, they are physical entities, they carry energy. This is really a very beautiful interplay between physics and geometry, because on the one hand, these gravitational waves are kind of ripples space-time, so it's very geometrical. On the other hand, they carry really positive energy. So then I just told you about the commonly used formulae and the literature, and one writes them, the same formulae are written as, instead of NAB, you write as a sigma dot squared, because N was just given by sigma dot. And then there is a second term that is coming in here, which is given, which comes from the second derivative operating on F. If you like, I can take this h squared integrated by parts and operate on F up here. And then for translations, this term disappears and we just get. So I got this flux formulae of how much energy and momentum carries away. This is where we were last time. And now I want to tell you about a key property, which is a Balance law. So the main interesting thing is the following, that we got this formula for fluxes, for this formula or this formula, which does not refer to any, this formula, which does not refer to any basis. I mean, I not use any tetrad, and bar, etc. So what turns out is that the total flux, you can write it as a 3 form. It's an integral of a 3 form. You can really show this, that's integral of a 3 form, and it is in the references I gave you last time. But this form is actually on Scala, that form is exact. On Scala, this 3 form that I get for the flux is exact. So the total flux, if I were to integrate to know what is happening to how much, I'm just interested in part of Scala and how much gravitational waves, how much energy or momentum or super momentum is carried away in this little region of Scala up here. So I got this formula, which will just say the same as before that we have got this formula that up here, except that instead of integrating on the entire Scala, I'm just integrating now from U1 to U2, from U1 to U2 up here. And then it turns out that because this is an exact 3 form, so it is a curl of a 2 form, and therefore by Stokes' theorem, this is just given, this integral of a 3 form is the difference between integral of a 2 form here and integral of a 2 form here. This is the potential, if you like, of this F. And this 2 form is I'm calling it Q. And therefore, is that some quantity evaluated here minus some quantity evaluated here is equal to the flux of energy momentum. And therefore, we can interpret the surface integral here at u equal to u2, for example, as the sort of energy momentum or super momentum at this instant of time. So that is why we get Balance law, which says that energy momentum or super momentum at this time is given by energy momentum, super momentum at this time, minus whatever the flux was of energy momentum, super momentum that left Scala. That is why it's called a Balance law. And this object, if I take C to be equal to just a super translation, then this is the this is called the super momentum. So in this case, it will be just called super momentum with this thing. So this object is just called super momentum. And therefore that super momentum is just given by integral of this 2 form, the integral of this 2 form up here. And then the statement is that I can work out what that is because I have explicit formula for the flux up here. And then it turns out to be precisely psi 2 naught plus sigma naught bar. And remember, so a real part of this psi 2 naught is what matters. And remember that the real part of psi 2 naught was just given by our asymptotic Y tensor plugged with LALB. So this is not the pullback, the asymptotic Y tensor itself with LALB. So the statement is that we got a nice idea, two surface integral, and it is giving us the super momentum evaluated at the retarded time u equal to u naught. And so, and the flux law says that the super momentum evaluated C1 minus the super momentum evaluated C2 is equal to the supermomentum that was radiated away in this region bounded by C1 and C2. And that is why it is called the balance law. And if we specialize to translations, then we got these alphas, and these alphas are there are 4 of them. So they give you the 4 components of the energy momentum. So the energy momentum of the 4 momentum evaluated at any one point, at any one time, which is one of these cross sections, U equal to U0, is just given by this quantity as before, except that now here instead of F, I got here alpha. And again, I have a typo there, so let me just correct it. This should be real part outside. Okay, so this is the statement. And now the important thing is that very fascinating thing, again, another interplay between geometry and physics is that we now have a notion of energy momentum of a system at any retarded instant of time. At this retarded instant of time, I got some energy momentum of the system. And there were powerful theorems that were proved in the 1980s, early 1980s, independently about the same time by Horowitz and Perry, by Ruela and Todd, and Schoen and Yao. I just wrote them in alphabetical order. And they show that this energy momentum is actually a time-like vector. Or if you like, the energy is actually, which is a time component of the 4 momentum, is actually positive. I mean, because of the minus plus plus signature, to get the energy, we have to put a minus time-like Killing vector field here, or time-like unit time-like vector field vector here, and into the momentum is a time component, but because of the signature, there's a minus sign. So this is positive. And this again is very, very surprising because the proof is completely in terms of differential geometry, but it is really telling us about something about deep about physics, that the total energy is positive. Now, I want to emphasize that this is not something that is obvious, because in Newtonian gravity, for example, the potential energy in gravitational field is always negative. So if you had more and more concentration of matter, then you might think that the potential energy might be so negative that the total energy would be positive. The mass, rest mass plus the energy could be also negative. And that does not happen in general relativity. The total energy, which includes the energy of the matter plus radiation, etc. But what is left over at this instant of time? So you had some energy momentum here, some radiation passed, and you're left over with some energy momentum at this time. So that is time-like. It's a very powerful theorem that was shown in the 1980s. And now the interesting thing is that, again, as I said, that we got this balance law. So we knew that the flux is positive, and so the flux is positive, energy that is carried away is positive, but the energy momentum, sometimes it's called a charge integral, just because it is a two-surface object. So if you like, it's the energy is considered a charge, or momentum is considered a charge. So, or angular momentum is a charge because it's the two-surface integral. So that is also positive. So gravitational waves carry energy and momentum, but they cannot carry so much energy that at the end of the day, the total energy of the system is negative. So even if you went all the way to I plus, the energy can go to 0, but it cannot become negative. So that is really very interesting, very important, and very non-trivial fact that was not at all obvious from Einstein's equations. When Einstein discovered the theory, of course, he had no idea that these beautiful properties hold. And in fact, even when he died in the 1950s, he did not know that the total energy is positive. And this is a very beautiful theorem that I got up here. And then there is a non-trivial agreement, because most of you probably know that we can also just take a space-like surface up here, which I'm calling here T equal to constant surface up here. T equal to constant surface. And with this, we can do the Arnovit-Desarnez treatment. So there also, what we're doing is we're taking some two sphere, and that look at the energy that is in this region enclosed by the two sphere, and take the limit as this radius goes to 0. So therefore, at I0, we have this ADM 4 momentum up here, And the very non-trivial statement is that not only, although their expressions look quite different from each other, here is the expression. The statement is that the path limit of the Bond-Diffour momentum as u naught goes to minus infinity, this u equal to u naught. I got some Bond-Diffour momentum here. If I take the path limit of this, then that is equal to the ADM-4 momentum. The reason why this is non-trivial is because to obtain the Bond-Diffour momentum, we went to infinity in the null directions. To obtain the ADM-4 momentum, we go to infinity in the space-like directions. So it's not obvious that the two things will agree, but again, it's a beautiful geometrical fact that they do agree with each other. Already, it is true that the gravitational waves actually and electromagnetic waves, they all carry positive energy, but even if the total energy is positive, this is another positive energy theorem that was shown that the ADM energy is also positive, and the radiation carries away energy, but it cannot carry away so much energy that you are left with negative energy. The total energy here is positive and the total energy here is non-negative. It may be zero, all the energy may be radiated away, but it never becomes negative. So that's really very beautiful feature of general relativity. So this ends our first part, which has to do with the conceptual and mathematical issues that are normally associated with gravitational waves. And I did this because it is very non-trivial how to describe gravitational waves in full nonlinear general relativity. We need Scri, we need the BMS group, we need the derivative operator, shear, psi4 naught, and all those things. And that is really the foundation of everything else that we are learning in this course, because that is what you mean by gravitational waves. That is what you're detecting and so on. And in these last two lectures, today and tomorrow, we are going to go to the application of this thing. We're going to use the balance laws that I just told you about. They can be used as diagnostic tools to test the accuracy of the waveforms and to improve the waveforms. Now, as I said last time, that normally one uses numerical simulation to evaluate the accuracy of the waveforms. But the statement is that we don't have numerical simulations for all the regions of the parameter space. We only have in some regions of the parameter space. And therefore, there are regions where the simulations are very sparse, so we do not know what the answer is. And however, these tests don't refer to numerical simulations. So we will know if you give me any waveform, I will be able to use this balance law in a way that I will explain today and tomorrow to really find out if the waveform is accurate or it's not accurate. And furthermore, numerical simulations themselves are certain approximations, and therefore these waveforms they can be used as the waveforms can be the balance laws can be used to test the accuracy of the numerical waveforms themselves. So that's what we're going to do now. That namely, the last two lectures have to do with balance laws as diagnostic tools for the waveforms. Now, all of you must have seen these pictures 100 times during the summer school. And the most famous event is the very first one, which is very loud. We're lucky that we found it. And then here is a strain. And that is really, this was in the Hanford detector in the northwest of United States. This is the Livingston detector in Louisiana in the southeast of United States. And this is the, and then the statement is that one can actually compare the two things. And the statement is that the data is compared with theory. So, and the statement up here is that the data is compared to theory, that works very well. And that is why we knew that when we observed the collision of two black holes and could tell about what kind of black holes they were, how much mass they had. We could estimate the spin, and we could also estimate the masses and the spin of the mass and the spin of the final black hole. So the spectacular discovery of compact binary coalescence, two compact objects merging with each other, and they go around, and that is why it's called coalescence. By the gravitational wave observatories, it was possible using what is called match filtering method, and I imagine you must have heard about this quite a bit in other lectures in this summer school. So the basically point is that what you do in this matching is that you got theoretical waveforms and you got this strain. So theoretical waveform is just this that we have been talking about many times. The shear, that is a theoretical waveform. And then the strain is exactly this. So I should just write it up here. So this object is the same as strain. So this is what I've actually seen, observed. When LIGO detectors, which is strain, that is what is really observed. So we calculate this theoretical waveform. So what you're given is, you're given the initial system. The initial system is two compact objects, either black holes or neutron stars. They're very far away. Let's suppose black hole for simplicity. Then we can use the Einstein's vacuum equation. With neutron stars, you have to use the equations with matter, much more complicated problem. With black holes, it is just vacuum equations. And so you're given some initial parameters, and these black holes go around each other and they lose energy, as we just saw. And because they lose energy, they shrink. Their orbits shrink, they come closer and closer to each other, and finally they merge, and that is a spectacular event. The merger event is where a huge amount of energy comes out. I mean, during this in spiral phase, energy is emitted. The rate of emission is low, but the in spiral phase is very long. But in the merger, it's a very quick phase, but the amount of energy flux is very large. As you must have heard many times, that during this last merger phase, there is so much luminosity, so much energy flux that is emitted in gravitational waves that it is actually larger than the energy flux emitted by all the stars in the universe in the form of the electromagnetic waves. So it really is a very spectacular event, cataclysmic event that occurs up here. And then we observe these waveforms up here. And as I said, that what we do is we match. This is the match filtering, meaning that we already put filters, namely we are looking for waveforms which are predicted by the theoretical models, and which of these does the observed waveform agree with any of these model waveforms. And if it agrees with some model waveform, then we go and say that, well, okay, what did that model waveform correspond to? What were the initial masses? What are the initial spins? What is the final mass? What is the final spin? And we say, oh, this is the event we observe. So the match filtering enables us to dig out signal from noise for the discovery phase, and then also to determine the intrinsic parameters, which are basically the masses and spins of individual black holes and the mass and the spin of the final black hole, and also other observables, as we will see next lecture. And also what is called extrinsic parameters, namely how far was the system, what sky location, at what angle with respect to the Earth this event take place, and so on and so forth. And there are also inferred observables, as I mentioned just now, the other observables we'll discuss next time. So the statement is that we need, in order for this discovery as particular, and also more importantly, to extract astrophysics, we need the theoretical waveform quite well to a sufficient accuracy. Now, one might say, okay, so we just calculate it. But of course, the problem is that in general relativity, we cannot solve the two-body problem analytically. We've got two compact objects, for example, two black holes or two neutron stars, neutron star, or a black hole and a neutron star. And this, we can have a merger or a coalescence of this binary system. They come in from far away, very far away, they're just going around each other. So in very far away, the two things are just going around each other. And then they lose energy, and therefore their orbit tightens. So they are actually going into small orbits which are tightening all the time. And then finally they merge. So there are three phases. And again, you might have heard this already, but I don't know if you have. Therefore, I want to emphasize this. Namely, you have got an in-spiral phase, you have got a merger phase, and then you have got the post-merger phase, in which the final black hole actually settles down. And while it is settled down, it is perturbed, it settles down to a black hole, so it still radiates. So we get radiation in these three phases up here. The inspiral phase is a long phase in which the two bodies, initially very far away, they spiral in. In this case, since they are far away, their relative velocity are small, and therefore we can use post-Newtonian approximation. In other words, we do a perturbation theory in the powers of V by C, starting with Newtonian orbits. So this is something that people do analytically. Then there's a merger phase, and this is the cataclysmic phase. So the inspiral phase is this phase up here. The merger phase is this big phase up here. And that is a cataclysmic phase. And therefore, in that phase, it is very violent, it is highly nonlinear. We need full general relativity. And therefore, that is done numerically. And in this case, at the end of the day, there is a single horizon, there is a single black hole. Even if initially there are two black holes, they merge. And then there is a single horizon. And a huge flux of energy or huge luminosity is emitted. And then this single black hole that we have just formed, it is still not equilibrium because it is such a violent event. So the black hole is formed, it is still very distorted. It does not look like a curved black hole at all. And it has to radiate away its multiple moments, as they say, and it settles down. And this is called quasi-normal ringing. And there's of the single black hole now. So here there are two black holes, here they merge. Now we've got a single black hole. And then there is a radiation that is emitted. This radiation is emitted as a black hole settles down to its final stage. And it happens quite quickly. And therefore here one can use perturbation theory around the final curved black hole. So you can think of this single black hole as being a perturbed curved black hole. This is a relativistic perturbation theory, general relativistic perturbation theory. Whereas here, we have the post-Newtonian perturbation theory. This is not relativistic. We've got V by C expansion. Here, we don't have V by C expansion. It is just the linearized gravity on the curved background. So we want to have a waveform which includes all those things. In most of the LIGO detection, the inspiral waveform is very well detected. The merger is very well detected. But the quasi-normal frequency part is not so well detected. It just has to do with the frequency window for which the LIGO is very, very sensitive, and the black holes that have been seen. If you have a black hole which is only few tens of solar masses, then the phase in which quasi-normal ringing happens, it is really very first few cycles lie in the LIGO bandwidth. After that, it's not in the LIGO bandwidth, therefore we don't see it. With advanced detectors, third generation detectors, they will be able to see this very quickly, very easily. And LISA will also be able to see this quite nicely. So the statement is that we would like a waveform which actually encompasses all these three phases, because only then we can compare it with the observations, the observed waveform, and see what event actually took place. Now there are many ways of getting waveforms, but by and large, LIGO is using these three main avenues in the data analysis. The first is called EOB, or effective one-body approximation. In this approximation, we do the following. Look at the inspiral phase. In the inspiral phase, there are two black holes which are going into orbit around each other, right? They're going around this orbit up here. And what we do is there is a technique. I mean, it's an approximation that even though it really is a two-body problem, we can think of it as being an effectively one body, which is moving in a gravitational field of the Schwarzschild space-time. So at first it looks like it can possibly not work because it's too crude approximation, but people are very clever and they used combination of methods, Hamiltonian methods, post-Newtonian methods very accurately. And then what they do is they do these post-Newtonian methods and they correct them by certain terms whose form they guess from the Hamiltonian methods, and the coefficients of those terms, they try to determine them by comparing the waveform that is produced analytically by this one-body approximation with the actual numerical waveform for a coalescence. And so you put numerical relativity input into post-Newtonian kind of analysis, but modified post-Newtonian analysis, and that actually gives you the waveform, and that is called the effective one-body approximation. The second technique is called phenom, and phenom just stands for phenomenological interpolation. So basically, there is the interpolation between the post-Newtonian phase and the nonlinear general relativity phase and the quasi-normal ringing phase. And what one says is that, well, there are some parameters, values of parameters for which we have this phase under control, this phase under control, this phase under control. And therefore, for those parameters, we actually just try to construct a waveform for the entire time, for the entire region, by doing interpolation between all these different phases up here. And this is very clever. I mean, it is a very phenomenological approach. It is not mathematical physics in the traditional sense of the word, but it is mathematical physics in the sense of fitting to data or fitting to exact solutions that one knows. And then one says that, well, I got this particular analytical expression, and then let me use that analytical expression also in the regions of parameter space where I don't have exact simulations. So I keep talking about parameter space. The parameter space is typically has internal parameters of the system. There are two masses and there are two spins, and therefore I got 6 dimensions coming from the 2 vectors up here and 2 coming from here. So the internal parameter is typically 8-dimensional. So it's a large space, and that is why it is not so easy to get numerical waveforms to fill this large space. And that is why what one does is I got this 8-dimensional space. Let me just figuratively think of this as being the 8-dimensional space, and I got numerical simulations here, 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 here. And what I do is I try to interpolate between them and get an analytical expression. So to begin with, I did not have I did not know what the waveform should be. Sorry. To begin with, I did not know what the waveform should be everywhere. I just knew what the waveform was here, 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 here. And what I do is I do an interpolation. So that interpolation will connect this trajectory. It's a very clever method. And therefore now this is the 8-dimensional space. And here I had no idea to begin with. I had no idea what the waveform should be. But by this interpolation, I know what the waveform is for these 8-dimensional parameters. So that is a general idea of this phenom models up here. I'm giving you references for those of you who are interested in actually following this up and understanding this in some detail. You can look them up. I give you plenty of references that you can choose whichever you want to look at. And finally, there's a third method, which is really does not look at post-Newtonian methods so much, but they just look at the numerical waveforms. And it interpolates, it does an extrapolation of the numerical waveforms. So I got some numerical waveforms at some points, and over here, the phenomenological models looked at the entire region up here, the in-spiral region, the in-spiral region, this region, and this region. And that is why this phenomenological model, often they call themselves IMR. And this IMR stands for in-spiral, merger, and ring down. This is a ring down up here. So this is called IMR. Whereas here, one is focusing mainly on numerical waveforms, and one is interpolating between them using extrapolating the waveform to other regions of parameter space where we do not have this numerical waveform. See, 8-dimensional parameter space is very large, and these simulations are very full nonlinear general relativity simulations, so they take long time. And that's why we need these interpolations. You could not fill the entire parameter space with numerical simulations. So here is a brief summary of the waveforms, and I'm just going to go quickly. So we got here post-Newtonian methods, and we got numerical simulations. And this is a very sketch. I mean, it's not a very detailed one, and it's not completely up to date, but it's up to date as of a year and a half ago. So the point is the following: that we need, a few hundred or 150 to 200 cycles in this waveform to correct. That's what LIGO would see, about a few hundred cycles. And therefore, the statement is that how are we going to produce them? And what one does is that we take about 100 of them are going to be quasi-circular orbits, which are given by the post-Newtonian expansion, and the last 10 or 15 would be given by numerical simulations. So these are done by numerical simulations. And therefore, as I just explained, then we got these other methods which combine techniques, the EOB method, the Phenom method, and the surrogate models, which give you then a waveform for the whole duration from the in spiral to merger to ring down. So, but of course, in order to do this, the statement is that one has to use many approximation, and there are guesses based on intuition and the choices that are necessary to resolve ambiguities. And here I explain a few of those choices that you have to make. So the post-Newtonian expansion is really obtained by doing the powers in V by C, and this should be V to the fourth, but I just could not get it in the program that I was using here to type these notes, and V by C to the fifth terms. So the statement is that if for results which are bigger than, for V by C, which is bigger than 0.2, when the objects are sufficiently close to each other, the contributions up to the V by C4 and if V by C to the 5 term, it turns out that they contribute, but they contribute in opposite directions. And therefore, the post-Newtonian expansion, really truncation is not so obvious, because you might get a result in which the quantity is growing, and then if I use the next object, then it actually decreases. And therefore, there are truncation errors involved as to you got post-Newtonian expansion and what order by V by C, but what n do you stop? So there is a truncation error. The second issue has to do with so-called Taylor approximants. Basically, the post-Newtonian waveforms are obtained by starting with the post-Newtonian expansions of energy of the system, E, and the flux radiated energy, V by C, F of V by C. However, because the procedure involves rational rather than polynomial functions of E of these quantities up here, there is some freedom in expanding these quantities to obtain a waveform to a given post-Newtonian order. And because of this freedom, several different post-Newtonian waveforms arise at a given order. And this is the so-called ambiguity in the choice of Taylor approximants. We've got rational functions and we're going to expand them out to given order in V by C, and there is some ambiguity in doing that. And then there is a third assumption, namely that one assumes that in the very distant past, the system is actually stationary. The black holes are so far away that if the radiations can be completely neglected, then it is really like a Newtonian orbit, in which case, it's like the Earth going around the sun. So it's a stationary object orbit. I don't have to worry about the radiation at all. But of course, there is always radiation, and therefore there is an approximation here. This is a very strong assumption to say that it's really stationary in the past. Then in the numerical relativity, we encounter other types of errors. The first is that there is there is always a truncation error in numerical, because the computer truncates up to say 12 decimal figures, but it has to truncate somewhere. Then there is a second is to extract the waveform. Well, the computer cannot really go to infinity, so you go to a large R and use instead of, if you like, this is scry, so you cannot go to scry, so you just go to some large R up here. So this is very large R, large, And actually you try to extract waveform up here. You cannot actually go to infinity. And the problem is that things like the psi4 radiation field, etc., those quantities are completely unambiguous at r equal to infinity, but at r the finite r, the tetras that are used and so on has some ambiguities, and therefore these objects also have some ambiguities of them. So therefore there are these ambiguities. And finally, one has to take the numerical relativity waveform, which is in the merger phase, and the post-Newtonian waveform, which is in the inspiral phase, and put them together. So if you like, in some ways, you have to stitch the two together to get a waveform which covers both these regimes. And there are ambiguities also in this stitching procedure. And again, you can see various references I'm giving you. And you have to make various choices. For example, the numerical waveforms are obtained in some coordinate systems, the post-Newtonian in some other coordinate systems, and you have to make sure that the two coordinate systems are the same, or they agree to the accuracy you want. And so you have to make many choices, and many of them are driven by intuition and past experience rather than clear-cut, unambiguous mathematical physics procedures. So I'm not saying this at all to say that people are sloppy or anything. They're very, very clever, incredibly clever. In a way, if there was a simple mathematical procedure, implementation of that procedure would be straightforward. But we don't have that. And these people have devised very, very clever methods in order to circumvent the difficulties of full nonlinear general relativity. So, but the important thing is also that the post-Newtonian expansion, the numerical relativity, they use very different conceptual frameworks. And you should know that, because people just go back and forth and students may not realize what is going on here. In post-Newtonian calculation, the sources are taken to be point particles in Minkowski spacetime. Or in post-Newtonian case, it's just Minkowski spacetime. In numerical relativity, there is no Minkowski spacetime. What we have is really two black holes. And the two black holes are represented by their horizons, which are evolving in time, they're dynamical horizons, and neutron stars with suitable fluids. In the case of black holes, the individual masses and spins are determined by the horizon geometry. Whereas in post-Newtonian object theory, these are just point particles. So they just have individual masses and spins that are assigned to them. And you can see we're using equations how they evolve. So the two things are not so obvious, right? What the relation is between the two things. One is really evaluated as a horizon, a finite distance up here, finite radius, and the other is just a point particle. What is the relation between the horizon and the point particle? Well, there's no clear-cut relation between the two things. And so there really is a point that in the final picture, the numerical space-time that you get has nothing to do with the post-Newtonian space-time you get. Post-Newtonian space-time at all orders in post-Newtonian theory is really Minkowski space-time, which is corrected, and then you got just point particles moving in Minkowski space-time. In numerical relativity, there is no Minkowski space-time, and you really have these horizons which are going around each other and finally merging. So conceptually, what one does, the space-times one has are dramatically different from one another. And yet, the statement is that what one can compare is really the final waveforms. And it is in these waveforms that this teaching procedure is done. And it is, the people are very, very clever, and they can actually, or have been able to obtain this reliable answers that, of course, LIGO has been able to use very well to do their detections. But nonetheless, these considerations make clear that even the 1% of the waveforms in the data banks that we have, which are obtained from post-Newtonian theory and NR, the remaining 99% are generated by this effective one-body method or by the phenom method, or the methods that I just mentioned up here, the surrogate method, the phenom method, and the EOB method, one of these methods. So 99% of them are obtained from that. But even for this 1%, there are inputs that we don't know. It's really a tribute to the physical intuition and the technical ingenuity behind these hybrid waveforms that the masked filtering procedure has led to this detection of these coalescing binaries. But what is happening is that, so here are the references and you can look at them. But there are two types of errors in all these things. One is to say systematic errors, and these are associated with approximations or well-motivated tricks used to create these waveforms. What we want is really to cover the 8-dimensional parameter space, and the computational speed is important up here. To do a computation, numerical relativity computation, which will contain more than 100 cycles that we need to do, it will take months. Last one took 8 months. Of course, we can't do that. We have to be much, much faster than that. And therefore, the statement is that some approximations have to be made, some tricks have to be done. So for example, you take psi4 naught, and you can do a spherical harmonic decomposition up here of that psi4 naught, and then that produces for you various YLM modes, and usually higher L equal to 2, of course, is the dominant mode that is taken, but L equal to 3 and higher modes are often ignored. Then a fast and practical way to accommodate precession, the two black holes, as they spin around each other, might be actually, as they go around each other, might actually be precessing. And this precession is not really taken into account using fundamental procedure, but by some, certain trick, which I'll mention next time. And then the way that the inputs from numerical relativity is included, all of them correspond to systematic errors. And next time we'll see what these systematic errors, how you can detect them using the balance laws, using exact general relativity. And then there are statistical errors, which are associated with the fluctuation in the detector noise and the necessary data analysis to extract signal from noise up here. But so far, luckily, the systematic errors have been smaller than the statistical error. And that is why, in spite of the fact that there are all these problems that I'm talking about from a purist point of view, there are all these problems, but these problems have not forbidden us from obtaining the confirming gravitational waves up here. So particularly for black holes in particular, the systematic errors are small than the statistical errors, and hence the models are adequate for discussion. But we will soon achieve much greater sensitivity on a significantly larger waveform. And then these systematic errors would be larger than the statistical errors, and therefore we need more accurate waveforms. The problem is at the moment, what do you mean by accuracy of the waveform, and how do you test the accuracy? And this really is a problem. And the point is that how do you test? Usually what people do is really they use numerical relativity, because they take numerical relativity as being exact. But numerical results themselves are ambiguities and assumptions. And therefore, the question that we want to ask is there a more objective way to test the accuracy of the waveforms in the template bank without knowing the waveforms themselves? And what we're going to see is really that this infinite set of balanced laws that we have got, that are made available at Scriplus, they provide us a natural answer. Whatever the exact waveform is, we don't need to know what it is. Whatever it is, it must satisfy the balanced laws, because the balanced law come from exact general relativity. So if you give me a waveform, if EOB gives me a waveform, Phenom gives me a waveform, I can just check if the balanced law is satisfied or not. If it is violated, in what way is it violated? And that will tell me how accurate that waveform is. And that is a beautiful interplay between mathematical relativity and these methods. I went a little bit late. I mean, 1 minute to 9:30, but it's just because I started 5 minutes late. But if you don't mind, if there are any questions, please do ask me questions. I will send you the transparencies for today's talk soon after the talk, but please do ask questions, either speak up or type them. I mean, this has to be very useful to you. And what I'm giving you is really filling in the gaps between various other lectures that you are hearing, and so that you can take this and and develop a global conceptual picture. So questions?
Okay, thank you so much, Professor Ashtekar. So as he mentioned, does anybody have question?
Yes.
Okay, please.
Hello, Prof. Ashtekar.
Yeah.
Thank you for your talk. Just want to ask, can you tell me more about the ambiguity and the inaccuracy about the numerical relativity method you mentioned? I'm not exactly following what you say.
Correct. So, for example, I mean, one of this will tell you a little bit more. The thing that I the typewritten thing that I said, and also there's some references that will tell you more. So, for example, in the numerical relativity waveform, some of the higher modes were not accurately detected, and there was a problem. I mean, for example, the modes which have to do with the memory, right? I'll explain this a little bit more, much more precisely next time. But let me just say that some of the higher modes were not accurately detected. Higher YLM modes were not accurate, and this is not accurate because there is high frequency noise that comes up in numerical simulations, and therefore and that they become worse and worse for higher modes. I mean, very roughly speaking, because higher modes correspond to YLM high, that means in the angular direction, the waveform is oscillating much more faster, and so on and so forth. And as a result, we'll see next time that right now it already has happened that with the input from the balanced laws, some of the numerical simulations, the template banks in the numerical simulations have been improved. And the references, yeah, I'll just tell you the reference, and you can look at that.
Okay.
More. Yeah, the reference is this reference up here. Mittman et al. Physical review, and the thing is this paper up here. So you'll see here how, looking at the so-called memory, looking at basically fluxes that I talked about, the fluxes of supermomentum between finite regions of Scri, delta Scri here, and then calculating them. There were discrepancies, and those were removed by looking at the balanced law. And next time we'll see that there are, for the angular momentum balance law, were found that there are some problems with, I mean, not serious problems, but still problems with numerical simulations, and the numerical community is looking at, in the Cornell Caltech group, is looking at them to fix them up. So basically, I mean, the errors are coming from the fact that one is truncating at a finite distance. When you're truncating at a finite distance, to calculate psi4. So psi4 was supposed to be was equal to KABCD times NA and B, NA and C and bar B and bar D. Now at Scri, these quantities can be defined ambiguously, but if I'm going to go inside, if I'm going to talk about somewhere here, right, some finite size, R large, but somewhere here, I mean, there's ambiguity as to what I mean by N, M, M bar, and so on and so forth. And therefore, this ambiguity is what I mean by psi4. I don't know exactly. So you're not going at R equal to infinity unless you do Cauchy characteristic evolution, which the data bank doesn't do. So there are problems coming in from that. The truncation errors are well documented, and they know what order they are, and they are much smaller than the statistical errors. There's no problem with that. So these are some of the errors in numerical relativity, and we'll see some concrete examples next time.
Okay.
Any other question? Any other question? Please go ahead.
Seems like there is a question in the
there is
chat
something
box.
on the chat box, right? Exactly.
Yeah.
How strong? Sorry, let me just read it. How strong can the loss constraint on the waveform in the template bank? I'm not expert on gravitational wave templates, but I would expect it is hard to satisfy some general requirement like the balance law. It is hard, is that? It is not hard to satisfy, right? In other words, it would be quite strange if the creator of the template failed to meet these constraints, and there are plenty of tunability in the numerical code. You are completely right. So what we're doing is really, so you're completely right that in fact, typically balanced laws are satisfied to good accuracy, but as you will see, they're not satisfied to all the accuracy. And therefore, what one is doing is one is finding bugs in some simulations. Something is not right in those simulations. And so people want to go back and check those simulations. I think the biggest thing was really the paper that I told you about, this Mittman et al., where they were able to correct one of the modes of one of the YLMs, one of the higher modes of these YLM modes. Actually, I think it was just Y20, in fact. The Y20 mode was very badly in the initial meaning before, until 2020, this was inaccurate in the waveform models. And that showed up by violation of the balanced law of supermomentum. And therefore, by looking at the balanced law of the supermomentum, they could actually go and fix it. So you're right. It's not that, the waveforms are just, going to be thrown out by the balanced law, right and left. No, but they will be scrutinized. They will be carefully looked at. Some waveforms may not be so good, and then some other waveforms will be quite good. So then one can look at the ones which are not so good, and people are typically gone back and looked at them and examined them and found that yes, they can be improved. So that is the goal of all these balance laws.